Hello, welcome everyone. In today's lecture, we are going to learn about internal reactions in 3 dimensions. So by the end of this lecture, you would be able to find out the internal forces and moments at specific cross-sections in 3-dimensional structures that are subjected to multiple deformations or multiple types of deformations. Okay? So if you think about internal reactions, so what are the internal reactions? Internal reactions are essentially reactions on a particular cross-section in a particular structure. So you have learned about support reactions in statics, for example. So essentially, if you have a structure, you can find out what are the forces and moments that are acting at the supports. So internal reactions are essentially forces and moments that occur within the structure. So essentially, if you take a structure and then take a cross-section and look at that particular cross-section and find out what are the forces and moments that are acting in that particular cross-sections, those are what are called as internal reactions. Okay? So when you have structures in 3 dimensions, okay, and these are subjected to arbitrary forces and moments, if you take a cross-section, you typically have 6 internal reactions at the cross-section. Okay? There are 3 internal forces and 3 internal moments. Now, if you look at the 3 internal forces, they are comprised essentially 2 shear forces, okay, and these are forces that act in the plane, and 1 normal force, which acts perpendicular to the plane. So if you want to think about the shear forces, you can essentially think of it as 2 forces that act in the plane that are perpendicular to each other. Okay? So essentially, these 3 forces are all, these 3 internal forces are all perpendicular to each other. Okay? Likewise, you essentially have 3 internal moments. Okay? And these internal moments act along 3 perpendicular axes. So typically, these are the x, y, and z axes. Okay? Of course, this is the most general case. Depending on the loading conditions, 1 or more of these internal reactions could be 0. So a couple of moment reactions could be 0, and 1 of the force reactions can be 0, or in some cases you might have just 1 force reaction, 1 internal force, and everything else is 0. So if you think of something like a bar that is subjected to an axial load, the only internal reaction or only internal reaction force is the normal force. The shear force are 0, and all the internal moments are 0. Okay? But in the general case, you have up to 6 internal reactions. Okay? Now, how do you find these 6 internal reactions? So usually you use the equations of equilibrium. So you have 3 equations of force equilibrium and 3 equations of moment equilibrium. So you use the 6 equations to find the 6 unknowns, which are the 6 internal reactions. Okay? Now, this is a little bit abstract, so let's actually look at an example on how to do this thing. Okay? So this is a case of an L-shaped beam, okay? And this beam is subjected to 3 forces, Fx equal to 250 pounds, Fy equal to minus 300 pounds, and Fz equal to 100 pounds at the point D. So this is the point D here, okay? You have an Fx that is 250 pounds, and Fy, which is minus 300 pounds, which means that it is acting in the minus y direction. So that is 300 pounds there, and an Fz equal to 100 pounds, which is here. Okay, so just to be clear, this axis here, that is your x-axis. This axis here, that is your y-axis, and that is your z-axis. Okay, so Fx is 250, Fy is minus 300, and Fz is 100 pounds. Okay. Now, we are asked to find out the internal forces and moments at the cross-section at point A, which is here. Okay. So the main thing that you want to know here is that you need to know the distances to find out what the moments are. The forces you can find without knowing the dimensions of the structure, but for finding the moments, you obviously need to know what the dimensions of the structure are. So the main thing that you need to focus on is that this distance from here to here that is 6 plus 3, which is 9 inches. And this distance here, that is 15 inches. Okay. So based on these forces and the dimensions of the structure, we are asked to find out what are the internal reactions at point A. So how do we go about doing that? Okay. The first thing that you always do is to construct a free body diagram. So what I have done here is that essentially I have taken this structure here, okay, and then taken a section at point A, and then I now consider this right half of this structure. Okay, so if you look at this particular figure here, I only consider the right half of the structure. Okay, because that is the structure for which I am interested in drawing the free body diagram, and using the free body diagram, I can find out what the internal reactions are. Okay, so now if you look at this free body diagram on the left, okay, you have the three forces that are acting at point D. Okay, and if I take a section at point A, that cross section is obviously going to have three internal forces and three internal moments. Okay, this Nx here, okay, that is the normal force. Okay, that is what you use for signifying a normal force, N. Okay, that's a normal force. For the shear forces, you usually use the symbol V. So this is a shear force. The same is true for this, which is also a shear force. Okay, so there are going to be two forces in the plane, and those forces are going to be oriented along the z-axis and the y-axis. Okay, again, just to remind you, this is my y, that is my z, and this is my x. So if I take a section, the normal to that section, in this case, is going to be the minus x-axis, and then of course you have forces along the z-axis and the y-axis. Okay, so the shear forces are Vy and Vz, and the normal force is Nx. Okay, and you also have three moments. The moments are obviously going to be along the x, y, and z axis, and I have drawn the moments here in such a way that the moments are all positive. Okay, how do you know these moments are positive? So if you think about mx, for example, mx is going that way. Okay, so how do I know that mx is positive? Okay, you use what is called as the right hand rule. So what you do is you curl your fingers along the direction of the moment and look at where your thumb is pointing. Okay, now if you do that in this case, if you curl the fingers along the direction of the moment mx, you will find that your right thumb is pointing in the positive x direction. Okay, you do the same thing for the moments mz and my, and you will find that the right thumb in those cases are pointing along the positive z direction and the positive y direction. So in this case, I have assumed that the internal moments that is acting at this particular cross section are all positive. Okay. For the forces, I have chosen different directions. So for example, I have chosen that Nx is pointing in the minus x direction. Okay, Vz is pointing in the minus z direction. Vy is pointing in the minus y direction. Okay, so I have chosen my forces or the direction of the forces in somewhat arbitrary manner, but for the moments, I have assumed that all these internal moments are along the positive x-axis, positive y-axis, and the positive z-axis. Okay, and the reason that you do this is because it is easy to get a sense of which way forces are acting, and you will find that force equilibrium is much easier than moment equilibrium. So as a general rule, you can essentially assume the moments that act in a particular cross-section are all along the positive x, y, and z directions. Okay? If it turns out that some of these moments are negative, it just means that the moment is in the opposite direction to what you assumed. Okay? So there is no rigid rule on how we have to assume these moments and reaction forces. But one thing that you have to be clear is that you must know what a positive moment is and a negative moment is. The positive moment, you get the sense of the positive moment using the right hand rule. So that is something you would have probably learned in your statics, but something that you need to remember again. Okay, so in this case, I have drawn the free body diagram. So let's go about applying the equations of equilibrium and finding out what these internal forces and moments are. Okay. Now, once you have this free body diagram, what I'm going to do is I'm actually going to kind of look at the equations of equilibrium. Okay, the first thing that you start with is the force equilibrium. Okay, because that is much simpler. Okay, so you start with the sum of forces in the x direction should be equal to 0. Okay, so that is this particular equation here. Okay, so in this case, you basically have only two forces acting along the x direction. One is this 250-pound force that is acting along the positive x direction. Okay, and you have this nx here that is acting along the minus x direction or the negative x direction. So 250 minus nx should be equal to 0, which means nx equal to 250 pounds. So what this positive value of nx means is that the force is along my assumed directions. Okay, so in this case, the normal force at that particular cross section is acting along the minus x direction. Okay, and it has a magnitude of 250 pounds. So you can do the same thing for the forces along the sum of forces along the y direction and the z direction, and you can find out what Vy and Vz are. Okay, so in this case, if you look at the diagram, I have assumed that my Vy is pointing downwards. Okay, the force that is acting at point D, that is also pointing downwards. Okay, so which means that my equation of equilibrium becomes minus 300 minus Vy equal to 0, which means Vy equal to minus 300 pounds. What does it actually mean? It means that the internal force at the cross section is not acting downwards, it's actually acting upwards. Okay, so I assumed a negative direction or the minus y direction for my internal force. It turns out that my Vy is negative, which means that the actual force is acting upwards. Okay, that's what it means. Okay, so that is my Vy, and of course my Vz is 100 pounds. Okay, so this is the easier part of the problem. Okay, now once you find the internal forces, you can now find the internal moments. Okay, there are two ways to find internal moments. Okay, one way you can do it is you can look at each of these components, mx, my, and mz separately, and find out what they are using moment equilibrium along the x, y, and z axis. You can also look at the moment equilibrium using the moment equation for the moment vector. Okay, so you can say that sigma m bar equal to 0, which means the vector moment m is 0. What essentially means is that each individual component, mx, my, and mz, if you sum them all up in each of those directions separately, they will all be equal to 0 separately. That is what the vector equation means. Okay, so what essentially it means is that your mx I plus myj plus mzk, which is essentially the reaction moment at the cross section. I, j, and k are the unit vectors along the x, y, and z direction. Okay, so the reaction moment at the cross section plus r cross f, which is the moment at that particular point, okay, or about the centroid of that particular cross section, due to these forces here, that should be equal to 0. So the internal moment plus the moment due to these forces about the centroid of that particular cross section, the sum of that should be equal to 0, because the moment about any point should be equal to 0. So in this case, we are just looking at the moment about the centroid of that particular cross section. Okay, now if you do that, you have mx plus mxi plus myj plus mzk, plus to find the product r cross f, the cross product r cross f, essentially you use a determinant. So essentially it's ijk times r, which is essentially the vector from the centroid of the cross section here all the way to the point where the forces are acting. So in this case, it's kind of convenient because all these forces are acting at the same location. If these forces are acting at different locations, then you have to find the R for each location and multiply, or take the cross product with respect to the force acting at that particular point. So in this case, suppose say you had another force that was acting here. Okay, then you will have to find R1 cross F, which is all these three forces here. Then you have to find R2 cross whatever force is acting there. Let's call this F2. Okay, so essentially you will have to do the cross product twice for each location where the force is acting. Okay, but in this case though, we are lucky that we have only one set of forces to consider and they are all acting at the same location. Okay, now you can find out what the R vector here is. It is going to be essentially 9 units in the x direction. Okay, so because that is 9 inches in the x direction, and it is 15 inches in the z direction. Okay, so that is why you have 9i and 15k. Okay, so that is your R vector there. Of course, they are all in the same vertical plane. So the component of the R vector along the y direction is 0. That is why you have a 0 here. Okay, and then of course, the third row is essentially the forces. The force at point D is 250 pounds in the positive x direction, minus 300 pounds in the y direction, and 100 pounds in the z direction. So that's why you have this 250 minus 300 and 100. Okay, so you do that, and this particular equation is equal to 0 vector. Okay, it is not a scalar, it's a vector, which means that all three components are 0. So the right hand side is 0i plus 0j plus 0k. Okay, all three components are actually equal to 0. Okay, so now if you do that, then you expand it out, the determinant, and then you find out what the value of the determinant is. It turns out to be 4500i plus 2850j minus 2700k, and that is equal to 0i plus 0j plus 0k. So essentially, all the individual components should be equal to 0, which means that mx plus 4500 should be 0, my plus 2850 should be equal to 0, and mz minus 2700 should be equal to 0. Okay, based on that, you can find out mx is minus 4500 pound inches, my is minus 2850 pound inches, and mz is 2700 pound inches. Okay, so based on our notation here, what it essentially means is that two of my moment reactions, okay, mx and my, both are negative, which means that the moment reaction of the cross section is in the opposite sense to what I actually drawn. So mx is not going this way, it is actually going that way. Okay, the moment at that particular cross section along the x direction is going that way. Okay, same thing for my. It is not actually going this way, it is actually going the opposite way, like that. Okay, whereas mz turns out to be positive, which means that my assumed direction is correct. Okay, it is just going this way. Okay, so essentially now we have found out the internal reactions, the three forces and the three moments. Okay, and this procedure can be generalized to any problem. Okay, so essentially you use the equations of equilibrium to find out the internal reactions. Okay, now in this case, I used the R cross F formulation to find out what the moment force or the moment reactions are. You can also look at individual components separately and find out what the moment reactions are. Okay, that we will do now. Okay, now in this case, it's the same free body diagram. Okay, the same forces are acting at point D here. Okay, and the internal forces and moments are assumed to be in the same direction. I'm not going to worry about the internal forces. I'm just going to focus on internal moments. Okay, let's start with mx. Okay. So this mx is a moment about the x-axis. Okay, so again, to remind you, that is your x, y is going vertically, and z is along the outward direction, which is along this particular bar. Okay. Now, if you think about mx, okay, how do you find out what a moment is? Again, you use the right hand rule. You put your right thumb along the direction of x and then curl your fingers. That is the sense of mx. Okay, so that is how I have assumed my internal moment at this cross section A to be. Okay, now let's think about what forces that act at point D are actually going to cause a moment about the x-axis. Okay, this is something that is very, very important for you to know. Okay, now if you think about this force Fx, which is 250 pounds, will it cause a moment about the x-axis? The answer is no. Because if you think about the moment, a moment is r cross F, which means that the moment is always perpendicular to the force. So if the force is along the x-axis, it cannot form or cause a moment about the x-axis. Because then, in that case, the force and the moment would be parallel, which is not possible. Okay? So this 250-pound force is not going to cause a moment about the x-axis. What about this 100-pound force in the z direction? Can it cause a moment about the x-axis? Okay? It is, of course, perpendicular to x-axis. So will it cause a moment about the x-axis? The answer, again, is no. Because if you think about this moment or this force Fz, if you extend its line of action, it is actually going to intersect with the x-axis. Okay? If the force intersects the axis of the moment, then that force also creates no moment about that particular axis. Okay? The reason is again the same. It is r cross F. In this case, r is going to be equal to 0, which means that the moment caused by the 100-pound force along the z direction about the x-axis is going to be 0. Okay. On the other hand, if this 100-pound force was slightly offset so that it doesn't actually intersect with the x-axis, in that case, it will cause a moment about the x-axis. But in this case, though, this 100-pound force, if you extend its line of action, then it intersects with the x-axis. Therefore, the moment due to the 100-pound force about the x-axis is also going to be equal to 0. Okay? So essentially, two of these forces, the 250-pound force and the 100-pound force, both of them are not going to cause any moment about the x-axis. So the only force that is going to cause a moment about the x-axis is the 300-pound force. Okay? And that is fairly simple. So essentially, if you think about this 300-pound force, that essentially will try to rotate the structure in this direction. Right? So what is going to be the amount of moment that it's going to apply? It is going to be this force times this distance, which is 15 inches. Okay? So mx here, as I've assumed, is along the positive x-axis. The moment due to this 300-pound force, that is also going to be positive about the x-axis, because you again look at how it is going to rotate the structures. You put your right hand fingers that way and then look at the direction of the thumb. It is going to be along the positive x-axis. So the force, the moment due to the 300-pound force about the x-axis is positive. The moment I have assumed at the cross section at A, the internal moment, that is also positive, mx. So essentially, mx plus 300 times 15 equal to 0, which means my mx is minus 4,500 pound inches. Okay? And that is exactly the value we got using the previous approach. Okay, so whichever way you do the problem, you will end up with the exact same answer as long as you have your notations correct. Okay, so now let's look at maybe one more component of moment. Let's say my. Okay, so if you look at the my, again, the internal moment at point A, I have assumed it to be positive along the positive y-axis. Okay, it is curling this way. My thumb is pointing up. So essentially, that's also a positive moment. Okay. Now let's try to figure out what are the forces that are actually going to cause a moment about the y-axis. Okay. The first thing we can rule out is that this 300-pound force can't cause a moment about the y-axis because the force is along the y-axis. So we don't have to worry about that. What about the 100-pound force? Will it cause a moment about the y-axis? The answer is yes, because the force is along the z direction. And if you extend the line of action of this force, it does not intersect the y-axis. Okay, again, I want to make sure you understand that we put this x, y, and z axis at the point where you're trying to find the moment, right? So if you look at this particular case, there is going to be an offset. Okay, it is not going to intersect with the y-axis, so which means that the 100-pound force along the z-axis is going to cause a moment about the y-axis. Okay, what about the 250-pound force that is acting in the x direction? That is also going to cause a moment because the force is in the x direction and it is offset from the y-axis. So there is going to be a momentum for the 2500-pound force as well. Okay, so essentially in this case, you are going to have a moment because of the 100-pound force along the z-axis and a 250-pound force along the x-axis. Okay, so what are these moments going to be? Okay, now if you think about this particular case, this 250-pound force here, okay, it is essentially going to rotate this particular structure. Let me actually use this like that. Okay, it is going to rotate the structure like that, which means that the moment due to that 250-pound force is in the positive y direction. Okay. On the other hand, if you look at this 100-pound force here, that is actually going to rotate the structure like that. And if you use the right hand rule, if you curl your fingers that way, the thumb is going to point downwards, which means that the moment due to the 100-pound force at that particular point and the cross section at A is going to be along the minus y direction. Okay, so now let's write out the moment equation for the equilibrium along the z-axis, along the y-axis. Okay, so you have the moment my, which is the internal moment at the cross section. Then you have the moment due to the 250-pound force, which is also a positive moment. So it's 250 times the distance here is of course 15 inches times 15. Okay, and you have a negative moment because of the 100-pound force. So it's going to be minus 100. And the distance in this particular case is going to be 9 inches. So it's going to be 100 times 9. And that should be equal to 0. Okay, so my is basically minus 3750 plus 900, which is minus 2850 pound inches. Okay, and if you go back and look at what we got, the exact same value. Okay, so essentially you can find the moments, the internal moments at a point, either using the vector equation for the moment, or you can look at each component of the moment separately and use equilibrium to find those particular components separately. Okay, either way actually works. Okay, and I would actually ask you to become proficient in both these methods, because each of them is going to be helpful in different cases. Okay, one immediate example that I can give is that, say if these three forces, okay, were not acting at the same point, each one of these forces were acting at different points, then you will essentially have to find the cross product 3 times, because you have to find R1, R2, R3, you have to find F1, F2, F3, then R1 cross F1, R2 cross F2, and R3 cross F3. Okay. So essentially, your work, or the amount of work you need to do, would essentially triple. But on the other hand, if you use an approach like this, essentially, you can look at all the forces that are going to cause a moment about the x-axis, sum them all up, and then you'll immediately get mx. Okay, same thing for my and mz. So in this particular case, when all forces are acting at the same point, it might look like doing this separately is more tedious, but that is not always the case. In many cases, it just makes sense to do problems this way rather than using the moment equation or the vector moment equation. Okay? So, and this one also gives you a good intuition on how different forces are bending or torquing the structures in different directions. Okay? And that intuition and the ability to imagine how these deformations actually happen is an important part of this class. Okay? So I would, really encourage you to get proficient in using both these methods to find the reactions. Okay? The last thing that I want to point out is that these internal reactions that we found are for a specific phase. Okay? So when I took a cross section, let me just use a different color so it's more apparent. When I took a cross section at point A and split this structure into 2 halves, okay, I create 2 surfaces. Okay. Now, the surface on which I have found the reaction so far is essentially the surface whose outward normal is the minus x-axis. Okay, so essentially if you think of this face that I found here, there is there's another face that is on the left half of the structure. Okay, what I am now finding, the reactions are for this particular cross section here. Okay, so if I look at that particular cross section, the normal to that cross section is the minus x direction. Now there is this other cross section which is the opposite of this, and if you look at that cross section, the normal to that particular cross section is the positive x direction. Okay, you might say that, okay, what is the big deal about this? It makes all the difference. Okay, so when you talk about the internal reactions, you essentially talk about the internal reactions on a particular surface or a particular plane. Okay, and you define the plane by the outward normal to that plane. So in this case, if you take a cross section at point A, if you look at the face whose normal is the minus x-axis, these are the reactions on that particular face, the one that we just found. Now, if you look at the opposite face at the exact same cross section, then the internal reactions are all exactly the opposite. Okay? So if you look at this nx, for example, we found that nx equal to 250 pounds. Okay? So in this particular case, the internal reactions is along the minus x direction, which is also the outward normal to the plane. If you look at the opposing face, then the nx in that particular cross section is going to be 250 pounds, but in the positive x direction. Okay, so if I make a cut and then split 2 surfaces, in this particular surface, my internal reaction is pointing out in the minus x direction. On this surface, it is pointing out, but the direction is now positive x. So what you essentially see is that if you put these 2 cross sections together, all the forces and all the moments will exactly cancel each other off. Okay? And that is how equilibrium is preserved. Okay? If the moments are acting in the same direction on both the faces, then you can't have equilibrium. The sum of more forces for this particular small section will not be 0. So this is something that is absolutely important. Okay, so you be mindful of which particular section you're looking at and what is the plane in that particular section that you're looking at. Are you looking at a plane whose normal is along the minus x or the positive x? Because when you plot moment diagrams or internal force diagrams or shear diagrams, you do it for a particular phase. Okay, so essentially if you say I'm plotting mz as a function of x, you're assuming that the normal to the phase that you're plotting these moments is the positive x-axis. If you do it for the phase whose normal is the minus x-axis, everything becomes the opposite. Everything flips around in their sign. Okay, so this is something that may look trivial, but something that is very, very important. This is something that you might have probably learned in your mechanics of material class, but you might not have paid too much attention to. But in this class, it is absolutely vital that you know the moments and the forces, internal forces, with the correct magnitude and the correct sign. Okay, I hope this is clear. But if not, essentially try to make up some of the problems on your own and then convince yourself that essentially this is correct. So one easy way to convince this is that if you look at this particular structure, what you can do is you can take a section at point A, but before you take the section at point A, you actually find out all the support reactions at this point O. Okay, so you find out all the support reactions at point O, then take a section, and now consider this segment. The left segment is the right segment. Okay, so in that case, you will be exposing the face at point A, whose normal is the positive x-axis. Now find out what are the internal forces and the internal moments at that particular point in that particular phase. What you will find is that the numbers are exactly opposite to the ones that we just found. Okay, it doesn't mean that your answers are wrong. They are correct, because in one case you're looking at a phase whose normal is the minus x-axis. In the other case, you're looking at the phase whose normal is the positive x-axis. Okay, so the numbers will be the same in terms of magnitude, but the signs will be different. Okay, so you should really take some time to do this problem both ways and convince yourself that what I'm telling you is correct. Okay, hopefully I'll see you in the next time and we can go into the meat of this course, which is about finding stresses under combined loading and so on. Okay.